Okay, welcome back to the final video of this lesson, of lesson 1. We're gonna ask ourselves what are magnetic domains, right? So if we were talking about why are magnetic materials attracted to magnets, we discovered that hey, these magnetic materials actually become magnets themselves when they are brought near a magnet. We call that magnetic induction. But how does that work? How does that work exactly? That's what we're going to discover when we ask ourselves what are magnetic domains. All right. So, theory of magnetism. What happens if I take a magnet and I cut it? Right? What do you think happens? Okay. I would show you a video for this. I'll show you a demonstration for this. But you know what? If I keep showing you videos, this lesson will take forever. So, you're just gonna take my word for it that when you cut a magnet up, what you actually get is that it becomes mini magnets. Each of these becomes its own magnet with its own north and south pole, and then this will be a north and south pole, and this will be a north and south pole, because you cut it here and you cut it here, right? So what happens if you were to cut it here and cut it here and cut it here again? You get a north-south chunk and a north-south chunk, right? Same here, north-south chunk, north-south chunk. And you'll see that this just keeps happening and happening and happening. Can you just imagine, use your imagination and you cut, and you just keep cutting until you cannot cut anymore. What do you get? You get little pieces of magnets, right? And so what can you conclude? You conclude that theoretically, okay, so if a bar magnet is cut into 3 smaller pieces, each become a magnet with a north and south pole. If we carry on cutting each magnet in smaller pieces, we end up with even smaller magnets. And theoretically, you see that one magnet is basically just made out of many tiny magnets, right? Almost as if the atoms are magnetic, and that's actually pretty much close to what is reality, right? That magnets are made out of this thing called so when you cut them up, each atom has kind of its own magnetic thing going on. Okay, as I was saying, each atom kind of is its own little magnet. With the let's represent the magnet with an arrow, with the arrowhead being north. Okay, so whenever you see these arrows where saying this is a magnet, the arrowhead is always north. Okay, so we look at this, and then these little magnets, atomic magnets, a few of them happen to always be pointing in the same direction. And they are kind of in these clusters, and these clusters we call them magnetic domains. So this is one domain, this is another domain, this is another domain. Okay, within each domain, the magnets always point in the atomic magnets always point in the same direction. Okay, but the domains can point in different directions because they are their own magnets. Okay, so sorry, this wasn't clear. This tells us that if you cut it up into smaller pieces, just keep cutting, then you get small little magnets, which suggests that each magnet is made out of mini magnets. Okay, and these mini magnets, we'll just call them atomic magnets and magnetic domains. So these whole things are magnetic domains. I hope that was clear. Okay, so magnets are made out of atoms, just like everything else. A magnetic domain consists of a group of atomic magnets pointing in the same direction. Okay, so when magnetization happens, what actually happens, right? So if you look at an unmagnetized bar, say this is a magnetic material, but it is not a magnet. Why is it not a magnet? Because if you look at all the domains, all the magnetic domains in the unmagnetized bar point in random directions. Can you see? They're all pointing in random directions. And so because they point in random directions, their effect kind of cancels each other out. So it doesn't act like a magnet. But when a bar magnet is brought near to an unmagnetized bar, what do you see happen? Suddenly, because this, let's see if you can follow this reasoning, right? These guys closest to the magnet, these are little magnets, right? So if there's a north pole here, we know that the south poles will be attracted to the north pole. So these will turn to align with this, right? They will turn to align with this magnet, where the south pole will be attracted here, the north pole will face the opposite side. When these turn, as a result, these will also turn. Does that make sense? Makes sense, right? So these turn, suddenly there's a very strong north pole here, very strong north pole here. So here will all turn as well. And you see that when you bring a magnet close, basically what you get is that all the magnets here, all the little magnetic domains here, will all turn to face the same direction. And when they all turn to face the same direction, what do you get? You get a south pole ultimately at one side and a north pole ultimately at the other side. Does that make sense? And so this also further goes on to say why the magnetic poles are strongest here and weakest and weak in the middle, right? Because actually they're all facing one side, right? So this is all very strong north, here is all very strong south. Okay, so let me see if there's any more. There should be a third one. So the magnetic domains point in the same direction, producing magnetism. North and south poles of adjacent domains cancel each other out. So basically these cancel each other, these cancel each other, these cancel each other out. So the main effect you're left with is this north and south pole of the whole bar magnet. Okay? The atomic magnets at both ends are free. This produces north and south poles at the ends, which is just what I was saying. Okay, not that important. The main thing is you understand that why this thing becomes a magnet, right? When you bring a magnet close, the main thing is that when you bring a magnet close, these will start to turn to align, which in turn turns to align everything, and so this becomes the poles of the magnet. Okay. Oops. Okay. If you notice right at the end, sorry, I can't erase this. Okay, if you notice right at the end, you notice that the poles fan out. Can you see what I mean by fan out? They're not perfectly parallel, right? They're not perfectly parallel. But you see that this group is a bit like that. This group is a bit like that. This one is also not perfectly parallel. This one fans out a bit. This one fans out a bit. Why does it fan out a bit? Because due to the repulsion between the like poles, right? Can you imagine here are all south poles, so they will repel. It's just like that question I did earlier about the paper clips. Two paper clips attracted, the bottom will repel each other, right? So in the same way, because the bottom here is all south, they repel against each other. The bottom here is all north, they repel against each other. So they kind of fan out a bit. Okay, this little detail will be important for you later on when you talk about magnetic fields, which should be the next lesson. All right. Okay, moving on. Yeah, just a meme for you. I don't know if you see this guy. Iron atoms in general, when it's not an induced magnet, they're just facing in random directions. But iron atoms in a magnetic field, everybody is aligned, right? So, yeah. Okay, so that is actually why magnetic materials become little induced magnets, because of this theory of magnetic domains, where the magnetic domains will all align, and then because they all align, they produce where everything is made of mini magnets, but they're all misaligned in general. When you bring a magnet close, they all align, and then it becomes a magnet. But what happens when you take the magnet away from this magnetic material? All these domains, they just turn to scramble and turn in their random directions again. Okay, but we'll talk more about that in the next lesson. What happens when you remove the magnet, right? What happens when you remove the magnet? That's actually the next lesson. Okay, so with that, we are done with this, sorry, and I will see you in the next lesson. Before you go, okay, so we're done. Why are magnetic materials attracted to magnets? Homework, really important homework. Section A, question 1 and 2, section B, question 1 and 3 of worksheet 18A. Okay, please take this down. This is your homework. And yeah, please do your homework before the next video, which I will hopefully send out in a couple of days. Okay, see you soon.